Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. We continue the development of radiation topic by starting with epsilon naught equation that we wrote in the last module, which was del square phi equals minus rho by epsilon 0, where phi is the electric scalar potential, which of course is related to the electric field. Okay. So, please note that there is no time here. Now, in general, these charges would be centered in space at some particular, they can be clustered around. So, I am assuming that there is a certain volume over which the charges are present, and this would be characterized by the charge density, which we will describe as having, as a scalar field, meaning that the amount of rho at different points in the space can actually keep changing. So, of course, I am assuming that there is some origin O, and then I am measuring the distance at any point onto this volume by the position vector r. Okay. Now, because I want to look at what is the potential at another point which could also have a potential, so which would also have a what is called the position vector r, I can't use the same r for both, right. So, I am going to call this volume where the charges are located, the position vector to the volume or the points within that volume where the point charges are located as r prime. Okay. The charge distribution will be referred to the charge distribution in the source. This r prime would essentially be the source coordinates, and this r we would call it as the field coordinate, meaning that this is the point where we seek the field. In this case, of course, we are seeking a scalar field which is potential from the knowledge of this charge distribution that has been given to us, and the material medium is assumed to be of permittivity epsilon 0. Okay. Now, for the single charge which has kept at the origin, let us say q, the corresponding potential at any other point away from the charge would be something like q by 4 pi epsilon times r, correct. If instead the charge is kept at r prime, then the potential would be actually r minus r prime, the vector distance between the two, right, the magnitude of the distance, which we are calling it as r prime, r minus r prime. So, this is for a single charge. Now, when you have multiple charges, then you can imagine that this charge can be written as rho r prime, which is to say that you consider a small volume here which is at a distance of r prime or the position vector of r prime times the small volume around this fellow, that is dv prime, that would give you the overall charge located in this small infinitesimal volume. Okay. And then the potential because of that would be rho of r prime dv prime divided by the same thing. I am assuming that this dv prime is very small, okay, point like volume is what I am considering. So, if I want to obtain the full distribution, I have to basically integrate this expression. So, I am going to get rho of r prime dv prime, this is the volume integral. So, I am going to write this as volume divided by 4 pi epsilon naught r minus r prime distance, right. So, this is what you are going to get as the potential at this particular position vector r or at the field point r, where the summation would actually come from many different charges that are located. So, the red line that I just drew actually tells you what is this r minus r prime magnitude. Okay. This actually has a very common letter that we use, which is given by capital R, and capital R would be the radial distance from the source coordinate to the field coordinate. Okay. So, this is the expression that you have. So, notice that this would be a volume integral in general, and it can be reduced to a surface integral if the charge distribution is actually on the surface. It could reduce to a line distribution if the charges are piled up along a line, or it could reduce to a point like distribution if the charge is an isolated charge or a bunch of charges located at a single point, right. So, all these different cases from the point charge, line charge, surface charge, and in general the volumetric charge is all taken care by this expression. Okay. I want you to notice two things. One is that there is an integration which is fine, but you notice that the integrated quantity inside is the source coordinate, while you keep the field coordinate r fixed. What you are moving or what you are doing is to kind of consider different r primes. Okay. So, at this point you have another r prime, and then you have the volume around that one, which we will call as dV prime, and then you look at the distance between that. So, this particular one, the newly drawn charge distribution, would be influencing slightly differently onto the overall field, or it will be contributing slightly differently to the overall field at the field coordinates. Okay. So, that I want you to notice. So, there is an integration, and the integration is with respect to the source coordinates. Okay. The second thing what I want you to notice is the appearance of this 1 by r minus r prime term. Okay. So, this is very important because as we will see, but not really derive, this quantity 1 by r minus r prime, or in general 1 by 4 pi r minus r prime, is what is called as Green's function for the free space. Okay. Green's function for the free space. If you are not happy with the terminology called Green's function, you can simply think of this as the impulse response, okay, of the free space. Okay. And now if you kind of look at this, this is kind of a convolution integral that is going on, right. See, what is your convolution integral? You would have some f of x, and then you have g of, or let us say f of x, and then the impulse response is usually some h of y minus x, right. So, this fellow would be the function, or whatever the convolution f of x convolved with, or f of y convolved with h of y, right. So, this convolution integral would have the function which is in this case acting like the field source coordinate, and then this fellow is acting like the field coordinate. So, this is exactly the same thing, right. Of course, I have not rigorously proven this, but the analogy should be essentially clear. The factor of 1 by epsilon naught in the case of the scalar potential, and a factor of mu naught in the denominator, or in the denominator of mu naught inverse, would be also multiplied to represent the Green's function for the scalar potential and for the vector potential. Okay. So, this equation that we have written is essentially a convolution between the source coordinate, or the source charges, or the charge distribution, okay, and this particular Green's function, which is 1 by 4 pi epsilon, or 1 by 4 pi r minus r prime. Okay. So, please note these 2 points. Okay. Why are they important? Well, we had this other equation which said del dot B equal to 0, and therefore, we wrote B as del cross A, correct. Now, I know that del cross H is equal to J, and I know that H is basically B divided by mu naught, correct. So, if I substitute for H in terms of in this expression here, I can write H is equal to B by mu naught. So, I will actually have an equation which tells you del cross B is equal to mu naught times J, or you can write this as J by mu naught inverse. Okay. You do not have to write it, but it is just another way of thinking about the denominator part being mu naught inverse for the Green's function, and it would be just epsilon 0 for the electric field Green's function. Okay. So, in any case, you have this equation del cross B equals mu naught J, and I know that B is basically del cross A. Therefore, I can write down the equation which tells you curl of A to be equal to mu naught J. Something interesting is going on here, because I can express this curl of A as del dot A minus del square A, which of course would be equal to mu naught times J. Okay. Now, what we have seen from vector analysis is that B can be expressed as the curl of A, but we have not said anything about what we should be choosing, or what we should be writing for del dot A. It turns out that this is under our control, and since this is under my control or our control, I am going to take del dot A equal to 0, gradient of 0 is also 0. So, I get a simplified equation which says that del square A is equal to minus mu naught J. Isn't this equation very similar to del square phi equals minus rho by epsilon naught? Yes, it is very similar, except for 2 differences. One, you are dealing with a vector field quantity, here you are dealing with a scalar field quantity. Here the source is a vector field, here the source is a scalar field. Okay. However, in the Cartesian coordinate systems, at least, this del square operator can be applied separately to Ax, Ay and Az, okay, which would then give out minus mu naught Jx, minus mu naught Jy and minus mu naught Jz, being the Jx, Jy, Jz being the 3 components of the current densities along the x, y and z. So, these are the fields. Okay. In general, Ax will be a function of x, y, z, Ay will be a function of x, y, z, Az will be a function of x, y, z, as well as Jx, Jy and Jz. Everything is a function of x, y and z. But because the del square operator can be split in terms of operating on Ax alone, on Ay alone, on Az alone, in the case of Cartesian coordinate system, you have this equation. And if you just take this part of the equation, the solution of this equation is very simple. It would simply be Ax at any field coordinate which is given by r will be given by integral of j of r prime, or rather Jx of r prime dv prime divided by 4 pi. Now, I will have to have a mu naught in the numerator, right. So, I have r minus r prime. Okay. So, this is the expression for Ax. In general, the expression for A will be obtained by simply removing this particular letters and then making instead everything into a vector field. Okay. So, if I take this entire thing as a vector field, then the vector field for the magnetic vector potential can be written in this particular manner, and this completes our solution for the magnetic vector potential. What is important is the direction of the magnetic vector potential will be the same as the direction of the J field. However, the direction of the B field will be perpendicular to the direction of the J field, right, because there is a curling operation involved out there. So, these are the two equations and the two solutions that we were actually looking for, and given that if the current distribution is known, then you can find A, and from finding A you can find out B. Yes, it is tedious in some sense, perhaps there is nothing we have gained from introducing this vector potential is what we will think of, but not really. I mean, in many calculations we can actually start with the vector potential, which simplifies lot of our calculations in calculating the fields of the radiation, right. The radiation fields can be somewhat easily calculated provided you start off with the current distributions and calculate the vector potential, and from there you go to the magnetic field. The reason why it becomes simple is because J and A direction coincide with respect to each other. Contrast this with Biot-Savart law. Okay. Biot-Savart law, now what I would like you to do is to go look up Biot-Savart's law, and then you will see that there will be a n cross j something sitting there in that Biot-Savart's law, meaning that you are actually going to look at this direction, right. So, that would actually also, that would not be in the same direction as the J field. B and J are not in the same direction as the J field, right. So, because of that, the calculations using Biot-Savart's law are slightly more complicated. Actually, very simply write this as A of r. Okay. I mean, what we mean to say is that it's an easier method to calculate A and then calculate what is the magnetic field B. Okay. Now, all these things is actually okay for the static case, but I am not really interested in the static case. See, for one primary reason, let us assume that my current distribution is along this z direction, okay, and it is slowly now varying. Okay. So, I will assume that this is only Jz component and it is slowly changing with respect to time, okay, and I am sitting very far away here. So, I am actually standing here or sitting here very far away from the source distribution, and I won't notice. So, let us say there is some source which has come, turned the current on and then turned the current off. Do you expect that this changing in the current, so if the current is actually turned to 0 and then suddenly turned on and then suddenly turned off, will you be able to see this sudden change in the current, or in general even if it is not sudden, it is a slow variation of the change, will you be able to see directly sitting at a distance r away? That is, the distance between these two is actually r, no, capital R, which is the distance between the field and the source and the field coordinates. I will not be able to say this because clearly if anything is changing, right, that characteristic will be visible after a propagation delay which is given by the distance between the source and the observer, or rather the source and the field coordinates, and divided that one by the velocity of propagation, right. So, taking the simple thing of the distance between them to be r and being in the free space, there has to be an at least delay of r by c seconds before this change in the current distribution is actually visible to me, right. But such a coding is not possible in this expression that we have written. I mean, where is the time dependence on this? There is no time dependence on this. So, therefore, we have to go back and look for what kind of a equation we should write such that the equation is valid for the time varying case, that is for the dynamic scenario as well. Okay. So, clearly in the dynamic scenario things are going to change slightly because del cross E is now no longer equal to 0, but you have minus del B by del T. Now, right away when you see this equation, your hope should actually extinguish of finding a scalar potential phi, because this scalar potential phi was valid only when the del cross E term was actually equal to 0. Now, because that is not 0, in fact there is a term which is minus del B by del T, clearly I cannot take this express electric field as a gradient of phi. So, what am I going to do with this now? Now, what we do is an interesting thing. I know del cross E is equal to minus del by del T and there is a B, right. Forgetting for the moment that I am dealing with the dynamic scenario, I will write B as curl of A. Now, I am actually guaranteed that this is okay, because the condition for defining B in terms of A was that del dot B was equal to 0, that is the B field had no divergence, which is true whether you are dealing with static or in the dynamic case, right. So, even when the fields are changing with respect to time, okay, when del dot B as a function of both space and time is equal to, because it is equal to 0, the corresponding B can always be expressed as the scalar potential A, except that the scalar potential A is now varying both with respect to R and T. Okay. So, you get this sort of an intermediate equation, right, and what we do now is that we write del cross E, which is now a function of both R and T, given by minus del by del T del cross A of R T, correct. I will put this onto the left hand side, interchange the operations of the curl as well as the time derivative here. So, I obtained del cross E plus del A by del T, this entire thing should be equal to 0. Okay. Now, because I have a curl of some new field is equal to 0, this field which is E plus del A by del T, I can express this as negative gradient of phi. Okay. Of course, this phi is now not just constant, it is actually a function of, I mean not constant, it is not time independent, it is now function of time as well. So, earlier you had this phi which was time independent, now the scalar potential is also time dependent. Okay. Of course, every quantity here in this expression is time dependent. So, I can rewrite this E in terms of a time dependent scalar potential, okay, as well as time dependent vector potential. So, now what you have actually seen here is a very interesting thing. See, in the static case this term would be equal to 0 and then we will not have this E being function of time and phi being function of time, they would simply be functions of R. But when time is not constant, you have this coupling term, right, and this coupling term that you have is actually the coupling term that is arising because of the current distributions. So, electric field is now being influenced by the magnetic field. Okay. Similarly, magnetic field will be influenced by the electric field because del cross H is having a component of del E by del T. So, in this way the magnetic field is influencing electric field in turn will induce the magnetic field. Of course, if you are interested only in writing what is B, then B can still be written as del cross A, right, and any variation of A with respect to time will change the electric field and via change the magnetic field by these expressions del cross E is equal to minus del B by del T. So, please do not lose of the fact that we have now graduated to the fields, but then we have this kind of a expressions out there. Now, there is an interesting thing that we want to find out. We already know how in the static case the general expressions for the scalar potential and vector potential are going to look like, correct. Now, what would be the corresponding equations for the scalar potential and the vector potential, so that we can solve them and find out the solutions in the time varying case. In order to answer that question, let us start with del cross H, which is given by J plus epsilon 0 del E by del T. See, the set of equations that we are about to write actually work better when we are dealing with the free space conditions. Okay. So, because we are in the antenna problems or in the radiation, we are interested in this scenario, we will continue to assume that we are dealing with free space with an epsilon 0 out there. Okay. So, I have this del cross H j plus something, there is nothing I can do with j, but for E I can use this expression and replace, and for B, now B is basically mu naught H, correct. Therefore, H is given by del cross A by mu naught. Okay. So, because I know that, I can rewrite the, I can include this H expression in here on the left hand side, and for E I can substitute here, right. So, after doing these substitutions, I get del cross A is equal to mu naught j. I hope we understand where this is coming from. This del cross A is coming from del cross A by mu naught. Now, I have multiplied that mu naught onto this side. So, that is coming from definition of H, and then del cross of that is already present. Okay. So, plus mu naught epsilon naught, which of course you recognize this as 1 by c square, and then you have so del E by del t. So, E is what? E is basically minus gradient of phi minus del A by del t. All these quantities are varying with time. Okay. Now, I can write down this expression as 1 by c square minus del square A by del t square minus interchanging the gradient and the derivative term. I can rewrite this del by del t of minus gradient phi as this particular quantity. Okay. I still have mu naught j, and onto the left hand side I can write this as del of del dot A minus del square A. Okay. Now, what I like to do is to kind of get inspired from the free space propagation equation that we wrote. In the free space propagation equation that we wrote for the electric field, we came across what is called as the wave equation, where you had del square of electric field E being equal to some constant of proportionality. In fact, that constant of proportionality was 1 by c square del square A by or del square E by del t square. So, you had the second order spatial derivative in terms of electric field being equated to the second order derivatives of the electric field with respect to time. Okay. You do have such a scenario in this set of equations. Okay. Observe carefully that you have this minus del square A term, which is the spatial derivative, being related to minus 1 by c square del square A by del t square in the time derivative case. Okay. What we do not want are these two quantities. Okay. So, I do not want this quantity, that is messing up my equations, and I would like to remove this one, but since this is the situation where we are actually dealing with the sources, we are actually trying to find out how radiation is happening, I cannot remove this. Okay. So, always keep this term here, because you are actually working with the case for finding the fields when there are current distributions and eventually charge distributions. The way to remove these terms which I have identified in this dashed lines is kind of very simple. What I do is I make this left hand side actually equal to the right hand side. Okay. What that actually means is that, let me erase this here and or write it here. Please note that I am writing this equality condition here. Okay. That is gradient of del dot A is equal to minus 1 by c square gradient of del phi by del t. Okay. Is it del phi by del t? Yeah, okay, this is del phi by del t, right. Now, because gradient is a common factor, I can put that outside and then pull the right hand side onto the left hand side. I get del dot A by plus 1 by c square del phi by del t is equal to 0. Okay. Now, one way of making the gradient of some field quantity equal to 0 is to set this entire thing itself equal to 0. So, I can write del dot A as minus 1 by c square del phi by del t. So, I actually have one equation here, and when I substitute that, I can remove this equation or this term from this equation. I remove this entire term here. Okay. So, what I now have is del t square. Del square A is present. So, you can pull this del square A by del t square back into this. So, this is 1 by c square, and then rearrange the equation. So, I am going to erase this, or I can first make this into plus here and a minus sign here, and then pull this fellow onto the left hand side. So, I now have del square A plus 1 by c square del square A by del t square which must be equal to minus mu naught j, okay. And then I have del dot A is equal to this equation. Finally, we can also show that there will be another equation for phi as well, which is basically del square phi minus 1 by c square del square phi by del t square, that should be equal to minus rho by, sorry, this is plus rho by epsilon 0, okay. So, that would be equal to plus rho by epsilon 0, right. So, this is another wave equation, except that in this wave equation the source term is the charge distribution, and in the previous case the source term for the magnetic vector potential is the current distribution, right. So, I will leave the next part as an exercise for you to find. I do not know whether there might be a plus sign or a minus sign, you can actually put whatever the correct sign here. So, I will leave this also as an exercise for you to figure out. But what I would like to stress is that if the right hand side were actually equal to 0, both the electric scalar potential, which is now time dependent, as well as the magnetic vector potential, which is of course also time dependent, both will satisfy the same type of wave equation, which means that it is possible for us to think of a sinusoidal excitation of the current distribution as well as a charge distribution, therefore leading to what is called as, what is the sinusoidal distribution for the magnetic field or magnetic vector potential as well as for the electric scalar potential, meaning that I can use the phasor ideas and convert all these time quantities into the frequency quantities, right. So, if I do that, for example, into this expression, what do I get? I get del square phi. Now, phi is a phasor that we are dealing with, plus omega square by c square, because remember del by del t goes as j omega, del square by del t square goes as omega square, times phi must be equal to minus rho by epsilon 0. Similarly, you will have del square A plus omega square by c square A to be equal to minus mu naught j. So, every quantity here is a phasor that I am looking at. So, this is also a phasor, this is also a phasor, this is also a phasor. Of course, omega square by c square equal to k0 square, and in the absence of the right hand source terms, the plausible solutions for A as well as for phi could have been e power minus j k0 depending on the direction of propagation. In general, the direction of propagation is along r. So, this would be e power minus j k0 r, okay. That is this the exponential phase dependence, but we are going to show this correctly, right. So, the equations that we have written are what are called as inhomogeneous or the equations are called as inhomogeneous differential equations, because the source terms are not actually set to 0, okay. They will complicate the solutions, but that is what the whole point of radiation is. We want to understand what kind of current distribution and what kind of charge distribution is going to generate a given vector field, vector potential as well as the magnetic potentials. Thank you very much.